Hello, welcome back. Today is lecture 35. In this new week, we'll discuss about silicon RF devices, specifically about highly scaled or nanoscale CMOS or MOSFET devices, which are also useful for RF application. So, in this week, we shall have 6 lectures going from 35 to 40, and we'll start with the basics of and the issues pertaining to highly scaled MOSFETs, and then we'll talk about SOI or silicon on insulator platforms for RF application, and then finally we'll talk about high voltage LDMOS, which is like the big brother of MOSFET for high voltage power amplifier application in the RF domain. Okay, so the slide over to the whiteboard here. So the assumption here is that you have been familiar with the basics of the classical silicon MOSFET, the long channel MOSFET, the gradual channel approximation, all the equations and the concepts pertaining to the long channel device operation. So, we shall not go through that. This is the basic schematic of a typical silicon or a classical silicon MOSFET. You know about the polysilicon gate, the drain contact, the well, the N plus P plus pocket, isolation using local oxidation LOCOS, which was the older generation devices, but this is all assumed to be known to you. So, what we are going to talk about in this series of lectures will be highly scaled or nanoscale silicon MOSFETs, because for state of the art RF or microwave application we need devices which are deep submicron in gate lengths. We need highly scaled MOSFET. So, this nanoscale MOSFETs have their own challenges and their own issues need to be addressed, understood and investigated. So, we will come to that directly. So, what does a nanoscale MOSFET mean and what are the issues with a nanoscale MOSFET? I will show you pictures very soon, but when I say nanoscale MOSFET in this particular course we are talking about something like say 90 to 32 nanometer node. Okay. Again, we have to understand that digital logic or memory or processor, which is basically the way that they define the technology node, 14 nanometer, 12, 7 nanometer, etc. That is digital logic. However, the things that we are going to discuss are predominantly oriented towards a platform that enables digital logic. However, RF devices or RF system on chips are also enabled or built into this the platform. The scaled platform that we are talking about here is actually for a logic operation or application. However, RF devices are also implemented there, because in a complete system you need a lot of RF operation also, mixing, oscillation, etc., in the backdrop of all this digital signal processing that might happen or the logic that might happen. Okay. So, right now we will not talk about silicon platforms that are specifically designed for RF, but rather we will talk about scaled MOSFETs in general, and we call them GP or general purpose MOSFETs. They could be useful for mostly logic, but also RF devices are implemented on them. Okay. So, typically we are talking about 90 to 30 nanometer node, 32 nanometer, because we are looking at RF application, we are not looking at digital logic here. What are the main features of such scale device? One is that people do not use this local oxidation for isolation anymore. People use something called shallow tranche implant, we will see that. So, this is to isolate the devices. People also use a retrograde well doping. Do you know what that means? Retrograde channel doping actually. So, the doping profile can change in the channel as you go from top to bottom. This is to adjust the threshold voltage and for many other reasons. People use high K dielectric nowadays, not just silicon dioxide. People use hafnium oxide based composite dielectric oxide for as a high K, and we will come to that also. People have moved from polysilicon gate to metal gate, okay, again for reasons that we will discuss. People have source drain extension. These are like the source and drain regions are extended slightly and they are very highly doped. People use spacer for self alignment. All these things will become clear as we discuss in an image going ahead. Okay, there is things like halo implant to reduce short channel effect, to engineer the doping profile, high doping in the source drain contact region. People use self aligned silicide to reduce all these parasitic resistances. People also use a channel stop implant on top of the STI. Okay, and people can use some liner film or some silicon germanium substrate to induce strain on silicon so that it can enhance the mobility, okay, and deep well of course. So, these are some of the key features of MOSFET when you scale them down to sub 100 nanometer gate lengths. Okay. So, let us take a look at the image here. So, you can see that in this image what we are looking at is a typical schematic of a nanoscale MOSFET. So you can see that this is the gate, of course. This is a highly doped source contact, that's a highly doped drain contact, and you can see that there is a slight extension here, that's the source drain extension. Okay, and you can see the shaded line here, that's the halo implant, which means there is a high doping of the same polarity, that is the p type doping. This is n plus doping, but this is p plus doping. Okay, high p type doping at the near the source and drain diffusion region, but not in the core channel. Okay, that's called halo implant. We'll come to that. This is your shallow trans implant, which basically is remove the silicon by etching, and then you fill it up with oxide. Okay, and then you planarize it to make it a planar process. This improves the isolation between two devices, and to further improve the isolation, people also give a p plus channel stop layer that will improve the isolation even better. Okay, and you can see that the gate is now, actually people use now metal gate for such highly scaled devices. To improve the contact resistance further, even for source drain, this is source, this is drain, even for gate resistance, people use silicide contact, could be say nickel silicide. Okay, so people use silicide contacts to improve the resistances, source drain, gate, etc. This spacer, okay, there is a oxide spacer and then there is a nitride spacer. This spacer defines how much self alignment you can get, because you are going to align with respect to the gate. The spacer will set the stage for the distance between the source and the gate, the source, the gate and the drain. So it's for self alignment. The final layer here, you can see this is a stress liner. This could be some kind of oxide nitride, silicon oxynitride, or some kind of other material which will help induce a strain on silicon, that is improvement for improving the mobility of electrons in silicon. Okay, when the silicon is under strain, it can improve the mobility. Okay, and these are, you can see the stall structures, these are via, these are typically tungsten via. What does it mean? You have multiple many layers of metal, metal 1, metal 2, metal 3, etc., because you are going to have integrated, a lot of devices are going to be integrated, and you are taking the current up, so multiple layers of metallization are required to take the current up, to have better integration. So you need to connect these different metals through tungsten. So these are called tungsten plug or tungsten contact vias that are used for taking from metal 1 to metal 2, metal 3, etc. Why tungsten? Because of its properties. For instance, it can withstand high temperature, it is very robust against electromigration, stability, etc. So people use tungsten contacts, it is very good. Okay, so this is like a picture of a schematic, general schematic of a say 65 nanometer, 95 nanometer planar bulk CMOS based nanoscale MOSFET, okay, which is also useful for RF application. When I am talking about RF application in the context of silicon nanoscale or highly scale planar bulk MOSFETs, here we are typically talking about low power, low voltage application, which is very enormous in number and scope. All kinds of mixers, oscillators, phase lock loops, frequency synthesizers, anything in the RF domain which are low power, low voltage on a circuit level, you need so many of them. You need a oscillator, you need a mixer, lot of times on all this circuit. So you can enable them using this kind of planar bulk CMOS based process, MOSFETs. You can implement them. Okay. At the 90 nanometer node, people actually started introducing strain engineering for mobility. So what does it mean? When you strain the silicon, in a way that, in a tensile way. So this is germanium, for instance. Germanium has a larger lattice constant. If you put silicon on germanium, you mimic the crystal structure below, of course with a certain limit on thickness. You can strain the silicon, you can see the silicon atoms have become strained, the bonds have become strained. So this strain gives actually rise to a modified band structure, or you can say a modified EK diagram that helps improve the mobility of electrons in silicon. Okay, people also use for hole, by the way. So you can see this is a bare picture of a silicon device, and this is with silicon germanium. If you have a silicon germanium base, on that you are putting a strained silicon, then your channel is going to have higher mobility, and that is very useful, because you will see that the mobility degrades very rapidly as the technology node is scaled down from 90 to 65, 45, 32 nanometer, etc. As you scale them down, the mobility degradation happens because of an increased vertical field in the channel, and to compensate for that degradation in mobility, people have adopted the strain engineering, and the germanium composition in silicon germanium also is increasing in order to accommodate more strain and have better offset for mobility degradation that is happening. At 45 nanometer node, people introduced high K dielectric. Why? Because when you scale the gate length, and if you have a gate length here which is Lg, and I have told this many times when you discuss compound semiconductor and gallium nitride, gallium arsenide, HEMTs and FETs also, then the channel, if this is your channel, the channel to your gate separation D, Lg by D should be at least 10, right, at least. In silicon it could be even, you know, for aggressive scaling it becomes even more challenging. So, for instance, if you have a 45 nanometer gate length, then the silicon dioxide that you have could be only around 4 to 5 nanometer, and what will happen is that the electrons can easily leak because of tunneling. Electrons can tunnel and leak into the channel, and that increases the gate leakage Ig, right. So, people introduce high K dielectric, say hafnium oxide. So, silicon dioxide has a dielectric constant of around 4, 3.9, and hafnium oxide, just for the sake of it, let us assume that it has a high K, its dielectric constant is say 24, 6 times higher. So, what it means is that you can actually have a layer of hafnium oxide, which is much thicker, okay, which is much thicker. You can have it 24 nanometer thick hafnium oxide, okay, will electrically be equivalent to just 4 nanometer of SiO2. So, your 4 nanometer of SiO2 is going to leak because of tunneling, because it is very thin. If you replace that with a very thick hafnium oxide of 24 nanometer, then electrons will not be able to tunnel, because 24 nanometer is a large thickness. However, 24 nanometer of hafnium oxide is exactly the same as 4 nanometer of silicon dioxide as far as the electrical behavior or the capacitance is concerned, because capacitance per unit area is epsilon s epsilon naught by the thickness of the oxide, correct. So, if your dielectric constant increases by 6 times, your thickness also can increase by 6 times in order to maintain the same ratio of capacitance. So, whatever capacitance you are going to get with 4 nanometer of SiO2 is precisely the same capacitance you are going to get with 24 nanometer of hafnium oxide. This is assuming hafnium oxide has a dielectric constant of 24. You see the point? So, people define this as an equivalent oxide thickness. So, equivalent oxide thickness, okay, this particular ratio that, you know, you are trying to keep the capacitance the same, that is the equivalent oxide thickness, okay. So, there is a definition for equivalent oxide thickness, which is basically what is the thickness of silicon dioxide that will be equal to say 24 nanometer of hafnium oxide. It is 4 nanometer. So, equivalent oxide thickness is 4 nanometer. So, equivalent oxide thickness is 4 nanometer for a 24 nanometer hafnium oxide, right. So, this is the equivalent oxide thickness, and for that people have used high K dielectric, okay, people have used high K dielectric, alright. So, that was as a high K gate dielectric. So, because of the strain, as I told already, because of the strain the mobility improves, and this is what is reported from literature, of course from industry also, that strain helps improve the mobility. You can see that this curve is for electron mobility, and you can see that this has electron mobility in a normal silicon, and this is the electron mobility for a strained silicon, strained to some extent. You can see that this is a 800 nanometer. As you are decreasing the technology node from 0.8 micron, 0.6 micron, this is 250 nanometer, 180 nanometer, 130 nanometer, maybe 65 nanometer. What is happening is that the mobility is dropping as a function of electric field, okay. In a way, with lower and lower technology nodes, like, you know, 65 nanometer, 36, 32 nanometer, etc., your electric field that the device will see is much higher, both laterally and vertically, but vertical electric field is much higher. Because of this significantly enhanced electric field at lower, or I would say the lower gate length or higher technology nodes, say 90 nanometer or 65 nanometer, because of a very high vertical electric field that the channel sees, your mobility starts degrading, and because of that, with higher and higher scaling, the mobility keeps decreasing, and that decrease in mobility is terrible, because that is going to impact your device performance. Your current will decrease, your transconductance will decrease, your excess resistances or parasitic resistances will increase, your cutoff frequencies will decrease, everything will be poorly affected, you know. So, that is why people use strain to actually boost the mobility up. The dependence of the mobility on the field still remains the same, the pattern remains the same, and the scattering phenomena in terms of acoustic phonon scattering or interface roughness scattering also remains same, but the absolute values of mobility are pushed because of the strain, okay, because of the way the conduction band diagram or the effect, the EK diagram is modified. You have this improvement in mobility, and that's the behavior is, by the way, same in general, the trend is the same, okay. So when you talk about gate length here, it is important to pause for a second and then understand what different gate length terminologies mean. So typically when you talk about gate length, we mean this length only, which is the physical length of the gate. This is the length of the gate metal or the polysilicon gate as defined at the foot of the channel. So this is your foot of the channel. So this is your physical gate. This is your actually electrical gate length, because the source and drain kind of comes, there is an extension, source and drain extension. This is called source and drain extension. Okay. So the source and drain are extended little bit towards here, and what happens is that your actual electrical channel length is lower than the physical channel length, but we talk about this typically. And this is your lithographic length, the length defined, this is the length of the gate that your lithography or the mask will define, keeping in view the self aligned process. But what you deposit metal is only over this, and what you get electrical is only over this. Okay. So there is this shallow source and drain extension, because of which you have even a reduced electrical gate length. Okay. So in sub 100 MOSFETs in general, again this is in general, okay, people had gate leakage issues, and that is why at 45 nanometer they adopted high K dielectric. There is also a large subthreshold leakage because of a low threshold voltage, because your threshold voltage keeps reducing. Okay, your subthreshold leakage becomes high, because your threshold voltage can become very close to 0 volt. So your subthreshold behavior will also change. You will have significantly increased subthreshold leakage for a highly scaled device. As I kept telling you, because of a high vertical field, your mobility degradation will become worse, because a high vertical field will lead to more interface roughness scattering. Okay. Because of a high vertical field, the electron, the wave function will be pressed hard against the interface. So the interface roughness scattering becomes more predominant over acoustic phonon scattering, which are the two main dominant scattering mechanisms. So mobility will degrade because of a large vertical field. There is also geometry dependent strain mobility. The way you define the device geometry, we will see also can define the strain that you have, the mobility that you have. Okay. The device geometry is very important in actual design. So one has to take that into account also. And then there is something called capacitive effective thickness. The capacitance that you actually get between, say you have a gate, you can have a metal gate for instance, and then you have SiO2, and then you have inversion here for instance, there is an inversion that forms here. This capacitance that you can get here, okay, which is just the oxide capacitance, ideally it should be just the oxide capacitance. It actually is not the oxide capacitance because of some other reason. There is charge quantization, and there is this quantum capacitance that comes in, we will see that. Okay. This increases the effective thickness of the gate to channel, and that reduces the total gate capacitance. So reduced gate capacitance also means the channel has a relatively lesser control on or poorer control on the channel. Okay. And so this is not a good thing, though. I mean, although you want to reduce the parasitics and reduce the overall RC delay, but because of this charge quantization, you have a capacitance which is actually smaller. Okay, you have a capacitance which is actually smaller, which is not desired per se. Okay, because you are losing control on the channel. Okay, so this is something we will come and discuss very shortly. The charge quantization effect. Okay, so the most prominent short channel effect, and again this have been discussed, I am sure this has been understood and studied in your basic semiconductor devices course, where people talk about the generic long channel MOSFET. People do talk a little bit about short channel effect. So this phenomenon has been studied in that, I understand, but I will just recap it nonetheless. The most prominent effect of a short channel effect, when you scale the device down, is that the threshold voltage Vt reduces with a reduction in the gate length. When you shrink the gate length down in every technology node, your threshold voltage keeps reducing. Okay. Why? As you can see in this figure below, the charge below the gate is precisely the channel charge that you are going to invert or deplete or whatever. So you can see that as you shrink the channel down, as your gate length Lg keeps shrinking down, the depletion from the source drain, this is the depletion region from the source drain. This depletion from the source drain occupies a certain extent of the depletion below the gate, correct. So what the gate actually can control is only this. It turns out to be not a rectangular profile, but like a trapezoidal profile. Okay, I am not drawing it here. It is like a trapezoidal profile because of the fact that this source goes like that and the drain goes like that. So you have a trapezoidal profile that comes up. So what it means is that the gate starts to see a lower and lower fraction of the total channel charge to control, because the source and drain depletion occupies a significant chunk of the depletion below the gate as L keeps decreasing. If your length is very large, like few micron, 3 micron, 5 micron, then this depletion region width does not matter, it is negligible. But if you have like a 65 nanometer or 90 nanometer device, then this depletion region can be substantial, in such that the gate now has a reduced channel charge to control, because a part of the channel charge has been taken by the source and drain depletion region. Okay. So because the gate sees a reduced channel charge, okay, your threshold voltage has reduced, because the charge below the gate is low. So if you plot the threshold voltage as a function of the gate length, so at higher gate length the threshold voltage is constant for a constant device parameter or dimension, but even with that, with lower gate length the VT will start dropping. So that is called VT roll off with respect to L, the gate length, and this is a classic short channel effect that has to be mitigated. So to mitigate it, what people do is that there are two things. One is that the depletion width below the channel maybe I can remove the annotation here. What people do is that the depletion width below the channel, this part has to be this depletion width has to be less than 1 by 3 of Lg, if this is your Lg. Okay. I mean that is your electrical length, actually the physical length is this is your physical length. So it has to be less than 1 by 3 of Lg. So it has to be less than the physical length of gate. How do you make that depletion below the gate less than 1 by 3? By using a retrograde profile. What does a retrograde profile mean? The retrograde profile means that in this direction the doping increases. So near the silicon dioxide interface, doping is low. As you keep going down, the doping increases. So it is a retrograde profile. So low doping on the top and then high doping at the bottom. You gradually increase the doping, So that is called a retrograde doping profile, because from the bottom to the top the doping is actually decreasing. So that doping profile is found to have reduced depletion. Okay, you have the depletion width in this direction, this depletion width X depletion actually is lower in that retrograde profile, and it can be tuned to be lower than 1 by 3 of the gate length. The second thing is that the source and drain junction depth, this also should be less than 1 by 3, but if it is too low in like 1 by 3 of Lg, your source and drain contact resistance will be very high if it is too shallow. So to compensate that, you have to dope it very high, because the thickness of this source drain doping, so Ts into the doping has to remain constant. So if your thickness is reduced to less than 1 by 3, then your doping has to increase proportionately to maintain the same the conductivity of the material, in a way we can say. Okay, you can say that you have to maintain the same conductivity here. So now there is something called a reverse short channel effect. See, when you reduce the gate length, the source and drain depletion regions keeps coming closer to each other. At the limit, when they come very close to each other, they can even merge. The depletion from source and drain can merge together, and if they merge together, it's called punch through. Depletion from one side and the depletion from other side, if they merge, then it's a punch through that will happen. Okay, and you do not want that. So to prevent the punch through, what happens is that a higher doping will reduce the depletion width, and a channel doping has to be higher. You see my point? So this doping, the doping in the channel, this doping has to be high. If this doping is high, then the depletion from the source and the drain side, the depletion from the source side or drain side will not be as much. If it is lightly doped, it will quickly be consumed by the depletion, but if it is heavily doped, then your source and drain side depletion will not be able to engulf or encroach too much upon the channel. Okay, so you need to increase the channel doping. However, if you increase the doping, your mobility will degrade, because mobility of electrons will depend on the doping density. Beyond a certain point, the doping density will rapidly kill the mobility. So that is why people use a halo implant. What is a halo implant? A halo implant is a doping profile such that the doping is higher near the source and drain diffusion region only. So near this region the doping is high. What doping? It is the well, the polarity of the doping is the same as that of the well. So this is a P well. On that you have an NMOS, correct, N channel MOSFET. So, your P type doping of the well has to be higher here and lower in the channel between. Okay. So, the only near the source and drain. So, essentially you have a source, you have a drain, you increase the doping of the well here, but you keep this doping low or moderate, you mean to say. So, the punch throw will not happen, the electrons the source and drain depletion will find it hard to deplete the highly doped region, and the channel mobility will not degrade because you have not highly doped it, correct. So, that is called halo implant. So, this has to be of the same polarity as the well doping, and it is a function of the channel length. So, this is how a halo doping looks like, this dot dashed line you can see. So, this is your source, this is your drain for instance, So, your doping profile is higher towards the source and drain and it is lower in the center. Okay. This is the P type doping, the doping of the same polarity as the well. Your doping profile will be higher towards the source and drain, and in the core of the channel the doping profile will be low. This is called a halo doping. Okay, halo doping. So, what is reverse short channel effect? See, the thing is, because you are doing all these techniques, you do not let the threshold voltage to decrease as gate length is scaled down. What happens is that the VT actually increases with the gate length shrinking down because you are using halo implant. You are taking all these approaches to prevent a VT roll off. So, your threshold voltage actually increases with a reduction in the gate length initially. Eventually, at very scale gate length, short channel effect will predominate, it will dominate over this, and the threshold voltage will reduce with reducing LG. So, essentially this is a reverse short channel effect, because initially you are reducing, as you are reducing the gate length, your threshold voltage increases and then the threshold voltage falls. This is your VT, threshold voltage increase, and this is your x axis. So, as you are shrinking down the L, the threshold voltage might increase and then it will fall. So, this part is called a reverse short channel effect, and it delays the onset of short channel effect. That is all it does. It delays the onset because it takes some time for, it's for, when I say time, I mean to say some technology nodes will see that their threshold voltage actually is not dropping with scaling down. Okay. So, for a given process, mobility, output impedance, source, and SB stands for source and bulk. Okay, there is a body or a bulk. DB stands for drain and bulk. So, source bulk and drain bulk capacitances, they all become function of the gate length because you are using a halo implant, the channel profile doping, etc. So, this impacts the manner in which circuit designers are going to design the RF circuit. Okay. And we will see very soon, in a very clear terminology, by the way, is that no longer people can use Vg minus Vt, the overdrive, as a design parameter. People cannot use W by L also as a design parameter, because there are so many things that are changing for highly scale nanoscale MOSFET. The process variation will affect threshold voltage, for instance, okay, and that is a significant concern. Okay. So, people use constant current, I will show you that. A constant current is used as a design parameter, and once you know the current, people do not use W by L, but people use W, the gate width, and the number of gate fingers. So, you have many gate fingers. So, how many gate fingers you need, and what is the gate width you need, and how many fingers you need, 1, 3, 4, 5, 6, and the gate width. These are the parameters to actually play with that are provided to the device design, circuit design engineer. W by L is not used, Vg minus Vt is also not used. Okay. So, please keep that in mind. So, this is reverse short channel effect. Okay. This is the halo doping, and of course, drain induced barrier lowering is something that we all know. When you bring the gate length smaller and smaller, the source and drain starts talking to each other in a way that the drain bias will start influencing the profile of the energy landscape along the channel. So, for a long channel device, for instance, this is along the distance, your conduction band profile looks like that. Ideally, with your drain bias, it should not matter under the gate, under the channel, it should not matter, and that is why the current saturates like that, beautifully, because in this saturation regime, the drain voltage should not have any role to play in how the conduction band profile looks like. However, when you bring the source too close to the drain, submicron, deep submicron, 90 nanometer, 65 nanometer node, then the source, the electrons that are injected from the source will see a reduced barrier. It will reduce the base. This is a reduced barrier, this is a reduced barrier. When will they see a reduced barrier? When the drain voltage is increased. When the drain voltage is increased, ideally it should not matter, but it does matter for a highly scaled device, because as you increase the drain voltage, the electrons that are injected from the source towards the drain will see a reduced barrier, because the drain is able to pull the entire conduction band down below the gate. Below the gate, the drain is able to pull the conduction band down, and because the drain is pulling the conduction band down, the electrons will see a reduced barrier. So, electrons will try to go, which means your threshold voltage will reduce as the drain voltage increases, okay, and that should not happen. With higher drain, with any drain voltage, your threshold voltage should remain same, but that does not happen. Okay, so this is very important. This is called drain induced barrier lowering, and we have to keep in mind when you are discussing all of these things, that even in RF CMOS devices, your gate leakage and subthreshold leakage could be very high compared to in normal MOSFET, but it still is not a problem at all, because compound semiconductor like gallium arsenide, pseudomorphic HAMT or indium phosphide HAMT, HBT, silicon germanium HBT, etc., they actually exhibit similar or much higher leakage than 65 nanometer CMOS process, for instance. But these compound semiconductor devices like indium phosphide or gallium arsenide PHAMs are enormously successful in lot of microwave, millimeter wave applications, strategic sector, wireless communication, etc. So, the leakage that you can see in a highly scaled 65 or 32 nanometer CMOS platform should not be so much of a cause of a worry, because it is similar or higher to that of compound semiconductor devices. Okay. So, with that we will end our lecture here today, lecture 35, because we are just introducing the basic concept pertaining to a highly scaled nanoscale MOSFET. This is general purpose MOSFET, GP MOSFET, which is also or can be also useful for RF application. Okay. But going ahead, we are going to talk about some more specific aspects in terms of, say, parasitic resistances, parasitic capacitances, small signal model, etc. Before that, we will also talk about certain more issues related to nanoscale MOSFETs. Okay. So, thank you for your time. I will see you in the next class, which is lecture 36.